Why waste time in commute and spend a lot of money for NEET UG coaching? Parents, do you want your kids to achieve top scores in NEET? India's leading online NEET coaching, 100% success. NEET UG. TeenEinstein.com. At TeenEinstein, we focus on NEET coaching from Class 6 to Class 12. We think you'll like it. Our teachers are mostly PhDs in physics, maths, chemistry, botany and zoology with lots of years of teaching experience for Class 6 to Class 12. Thousands of videos, quiz, MCQs. We provide a daily worksheet of 30 questions on each topic, math, physics, chemistry and biology for rigorous practice, concept understanding, evaluation, quizzes and thousands of videos. Limited offer, 40,000 per year. Book your class. TeenEinstein.com. Contact 99402 49720.
Hello everyone. So in this video we are going to talk about current electricity. So in this video we are going to see these topics. First we will see what is electric current, then electric current inside a conductor, Ohm's law, then the drift of electrons and the origin of resistivity, limitations of Ohm's law, resistivity of various materials, and finally the temperature dependence of resistivity. In the previous section, when we talked about charges at rest, then we talked about the potential energy of dipoles and capacitors and everything. In all of these things what we discussed before, the charges were at rest. Okay, so now we are going to see what happens when the charges start moving. So this is what we call as current or electricity. Okay, so when the charges are moving, they are flowing, then they create electricity. So in electrostatics, all charges were at rest and charges in motion constitute an electric current. They occur in many natural phenomena like lightning is one such example, in which charges flow from the clouds to the earth through the atmosphere. But it is not a steady current. Why we say it is not a steady current is because it just happens in a short amount of time. The charges are flowing from one place to other place, but it is not a continuous event. So continuous event means if the charges are flowing continuously, like in this kind of a circuit. See, here you see a battery connected to an electric bulb. So the battery is or a cell is actually driving the electrons to flow in this particular circuit. So the electrons are continuously flowing in the circuit, giving rise to current in the circuit, and the bulb also glows. So this is an example of a steady current. But the thing that occurs in lightning is not a steady current. So these are the everyday appliances which uses electricity. So in everyday life devices, charges flow in a steady manner, like water flowing smoothly in a river. Okay, so what is electric current? How do we define it? We already talked about this. The electric current is nothing but the charges which are moving. So we will assume that there is a small area held normal to the direction of the flow of charges, like this. Let's assume that this is the area that is held normal to the flow of charges. So the flow of charges makes 90° with the surface. So the net charges flowing through the area in a given time interval is Q equal to Q plus minus Q minus. So we are going to consider how many net charges are flowing across this particular surface in one direction within a given time interval. So when we say net charges, then we mean that addition of charges, or we can say that mathematically we are adding the charges. For example, if 10 positive charges and 2 negative charges are flowing through this, then the final net charge is going to be 8 positive charges. So that is what we mean by net charge. So this quantity is proportional to T for steady current. Steady current means the current is not changing with respect to time. So that quantity means the amount of charge, that is amount of net charge that is flowing through this particular surface is going to be proportional to T, because if time is increasing, then the net charge which is flowing through will also be increasing in the case of a steady current. So the net charge divided by this particular time is the electric current through the surface. So this is how we define electric current. We define the electric current as the net charge flowing through this particular surface at a given time interval T. So we will just see how to write it mathematically. Let delta Q be the net charge flowing across the cross section of a conductor during the time interval delta t. Then the current at a time t across the cross section of the conductor is defined as the value of the ratio of delta Q to delta t in the time limit delta t tending to be 0. Okay, so we already discussed this. Delta Q is the net charge flowing across a cross section of a conductor in the amount of time interval delta t. So obviously the current is going to be delta Q by delta t. But since we are talking about what is the current at a particular time t, we need to minimize this delta t. Delta t has to approach 0. So this is the equation of current at a particular time t, I as a function of t. And current is represented by units, SI units, ampere. Okay, so we defined what is current. Now we will see what is the electric current in conductors. This is very important because we use this in our everyday life in all the appliances. We use copper wires, which is a conductor, and the charges are flowing through the conductor, and that's how we get electricity in our house. So this is very important. So an electric charge will experience a force when an electric field is applied. So this we already studied in the electrostatics. So whenever there is an electric charge, you apply an electric field, it is going to experience a force. So the electric charge is going to move with respect to the field direction. If it is a positive charge, it will move along with the field, and if it is a negative charge, it will move opposite to the field. It moves immediately if it is free to move. So this is very important. Like in a conductor, there are a lot of free charges, right? If you apply an electric field in a conductor, then what happens? The charges will move. This is what we talked about in the previous lecture also. When we keep a metal or a conductor in an electric field, we saw that the charges will move to the opposite directions and it will create an internal field. So the same thing happens here. So if you keep a conductor in an electric field, the charges will move if they are free to move. Bulk matter is made up of many molecules. In solids, these molecules are so closely packed that the electrons are no longer attached to individual nuclei. They are called conductors. So in conductors, when we say there is a piece of metal, it has all the atoms stacked closely together, or atoms and molecules closely packed together. When they are closely packed, the electrons which belong to the individual atoms or individual molecules are no longer localized. They will be free to move everywhere in the conductor. So now if you apply an electric field, they are free to move within this conductor depending on how which direction your electric field is. Conductors develop an electric current in them when an electric field is applied. So why we have these are called charged conductors, and they develop an electric current in them when an electric field is applied. So electric current means movement of charges. When there is no electric field, the free electrons in the conductors are randomly moving. So even when in the absence of an electric field, the electrons are free to move within the metal anywhere. So they will be moving, but they are moving randomly. So the net charge flowing across a particular area can be 0 because it's randomly moving in all directions. And they collide with each other and change directions randomly. So the net current is always 0 in the absence of external electric field. Okay, so now the average number of electrons traveling in any direction will be equal to the average number of electrons traveling in the opposite direction. So the net charge transfer is 0, so no current is there. This is in the case of no external electric field. In a conductor, the electrons are randomly moving. So if you take any particular surface, the electrons moving in one particular direction will be equal to the electrons moving in the opposite direction. So the net current is 0. And when an electric field is applied by adding plus Q and minus Q on charges on both sides of the cylindrical conductor. So we are assuming a cylindrical conductor which has a circular cross-sectional area. And you're keeping plus Q charges here and you're keeping minus Q charges here. So by doing this, we are creating an electric field inside this conductor. So the electric field goes from left to right as shown in the picture. The electrons will be accelerated towards plus Q due to the Coulombic attraction. This is how the application of the electric field gives rise to current in the conductor. So now all the electrons, free electrons in the metal will move towards the left because this has positive charge and the negative electrons are attracted towards it, and all the positive ions will be in this side. So this is how a current is produced when you apply an electric field. If the field is continuously applied, then steady current is produced. So this is not a steady current because once you put charges here, the electrons will move and then the movement stops after some time. But in the case of a steady current, if you constantly apply the electric field so that the electron flow is continuous, then it is a steady current. Okay. Now we will see what is Ohm's law. So we know what is potential difference. We already talked about this, and we know what is current now. So when you apply an electric field across a conductor, then there is current flowing in the conductor. So what is the relationship between these two? That is explained by Ohm's law. So a conductor with current I, V is the potential difference between the ends of the conductor. Ohm's law states that the potential difference V is proportional to the current I. So V is directly proportional to I always, and the relationship between them is defined by a constant R. So the proportionality constant is R, V equal to I multiplied by R. This is the statement of Ohm's law. So the proportionality constant R is known as the resistance of the conductor. And the SI unit of resistance is ohm. So resistance means how much the material resists getting electricity, resist the flow of electrons. So that is the so R is a measure of how much resistance the material is giving for the free flow of electrons within the conductor. So the resistance R depends on the material and also on the dimensions of the current carrying wire, length and area. So resistance means it depends on material. Different materials will have different resistance values or resistivity values. We will see what is resistivity later. So depending on the particular material, the resistance values will be different. That's why we use copper, and we can use any metal for conducting electricity. But why we use copper in our houses? It's because of its resistance values. And the resistance also depends on the length of the conductor and the area of cross section. So resistance is given by this relation rho L by A, where rho is the resistivity, L is the length of the conductor, A is the area of cross section of the conductor. Now we will just see how to derive this relation. So we will take two identical slabs of length L and cross-sectional area A, and we will just keep them side by side so that the length of the combination is 2L. So we will take one rod like this with length L and cross-sectional area A, and we will keep them side by side so that the total length is 2L and the cross-sectional area is still A. The current flowing through the combination is the same as the current through either of the slabs, because if, let's say, the charges are going from left end and they will be coming out of this end. So in between we are not taking any charges outside. So whatever charges goes through this will be coming out of this. So then the current flowing through this combination is the same as the current through either of the slabs. So the current is going to be same for both the slabs. Now the potential difference across the ends of the combination is clearly sum of the potential difference across two individual slabs. So if we say that one potential difference across one slab is V, then two slabs it's going to be V plus V, 2V. So the resistance of this particular combination is RC equal to V by I according to Ohm's law, and instead of V we have 2V here, 2V by I, which is equal to 2R. So what does this say? If you increase the length by 2L, length twice, then the resistance value also increases by the factor of 2. So the resistance is proportional to length. If you have, let's say if you have one more slab here, then again the resistance will become 3R. So the value of the resistance is directly proportional to L. So in this formula we got R equal to rho L by A. So we got why it is directly proportional to L. Now let's see why it is directly proportional to A. Now the slab is divided into two by cutting it lengthwise. So we take the same slab and we cut it lengthwise like this. So what we are doing here is we are cutting the cross section as we are reducing the cross section by 2. So the cross section, new cross section becomes A by 2. Now the current flowing through each slab is I by 2, because current is nothing but charge by charge going through that particular area. So if you divide the area by 2, then the current also becomes half. Now the current flowing through each slab is 1 by I by 2. So the total current is I. The potential difference stays the same. So it is going to be V. So the resistance of this particular combination, again let's apply Ohm's law. Resistance of this combination equal to V by I. And now I becomes I by 2. So V by I by 2. Now we have 2 multiplied by V by I. So which gives rise to the factor 2R. So now the for this particular combination, the resistance becomes 2R. So when the area of the cross section becomes half, then the resistance doubles. So this gives us this relationship between R and A as R equal to 1 by A. So R is directly proportional to 1 by A. And we will combine these two results. In the first we talked about L, so R is proportional to L and R is inversely proportional to A. So this gives us R is proportional to L by A, and we will add a constant, proportionality constant as rho. So this gives us R equal to rho L by A, and rho is nothing but the resistivity of the material. So resistivity here is an intrinsic quantity, unlike resistance. Resistivity is the intrinsic quantity of the material itself, and resistivity does not depend on length or area. But resistance depends on length and area, but resistivity is an intrinsic quantity. Okay. Now, the proportionality constant rho is called the resistivity of the material. It's an intrinsic property of the material and it does not depend on the dimensions. Now, Ohm's law can also be written as, we know what is Ohm's law. Ohm's law equal to V equal to I multiplied by R, and instead of R we have this formula rho L by A. Let's substitute it here. So V equal to I rho L by A. So now the current per unit area is called the current density. We are going to introduce another concept called current density. So I by A can be written as J. Okay. The potential difference across the length can be written as E by L. So where E is the electric field. So let's substitute these two things here. Now, so instead of V, we can write E by L, and instead of I by A, we can write J. So if we do this, then we get E equal to J multiplied by rho. So J is nothing but the current density, rho is nothing but the resistivity of the material. So if we define another concept called sigma, so sigma is nothing but 1 by rho. So let's just look at this equation E equal to J into rho and rearrange this. Keep J in the left hand side and bring rho to the right hand side. Now what happens? J becomes E divided by rho. So 1 by rho becomes sigma. Sigma is nothing but the conductivity of the material, which is the inverse of the resistivity. So sigma equal to 1 by rho. So now we have another form of Ohm's law. This J equals to sigma A is an important form of Ohm's law. So when we talk about Ohm's law, we can either write V equal to IR, or we can write current density equal to sigma multiplied by electric field. Sigma is the conductivity of the material and given by 1 by rho. Okay, so now we defined what is current, and we also talked about what is current inside the conductor, and we defined the current, and we also derived Ohm's law in terms of current density. Now we are going to get a closer look into the conductor and see how the electrons are moving inside the conductor and why there is resistivity in the material. We talked about it and we just said that there is resistivity, but now we are going to see why there is resistance inside the metal. So okay, we already know that if you take any material, there are a lot of atoms that are arranged in a crystals. So when these electrons are moving randomly, they collide with the atoms. So you imagine that there are many atoms and molecules kept closer together and the electrons are moving randomly. When the electrons are moving randomly, they are going to make collisions with ions. So when there is no applied electric field, then these electrons make collisions with the heavy fixed ions and will emerge with the same speed in random directions. If all the electrons are considered, their average velocity will be 0 since their directions are random. If there are n electrons and the velocity of the ith electron at a given time vi, then the average of the velocity is going to be 0 because they make random collisions and they keep changing the direction and they have the same velocity every time they make the collision. So if you take the average, it's going to be 0. But when an electric field is present, the electrons will be accelerated because now the electric field is driving the electrons in a particular direction because by creating a force. So now the electrons will be accelerated. Now what happens? How will we say that? How will we define this acceleration? Acceleration equal to F by m from Newton's second law. F equal to ma, right? So in this case, what is the electric force? Electric force is nothing but Q multiplied by E. And instead of Q, we have minus E here. So the acceleration equal to minus E by m. Now we know that V equal to U plus AT. From the mechanics, we know that V equal to U plus AT. So if you take this as final velocity of the electron after applying the field, if this is the initial velocity of the electron, then this is AT. So instead of A, you have minus E by m and Ti. So this is the final velocity. Now let's take the average of this particular velocity over n electrons at a given time t. So the average velocity, we will say that this is Vd. V average is equal to, we are just taking the average of that equation for all the quantities. So Ui, this is the initial velocity average minus At, T average. So initial velocity average is going to be 0 because before applying the field, the electrons were randomly moving. So the final velocity was 0. So the initial velocity before applying the field is going to be 0 minus E by m into Ti average. And instead of Ti average, we are introducing a quantity called tau, which is nothing but the average time. So now we have Vd, that is the drift velocity, equal to minus E by m into tau. Now this Vd is called the drift velocity. So it means that when you apply an electric field, the electrons are going to move with a particular velocity. That velocity is given by Vd, that is nothing but the drift velocity. So that is, if you see this equation, that is directly proportional to the electric field and it's inversely proportional to the mass of the electron, and it's directly proportional to the charge. Now, because of the drift, there will be net charge transfer across any area perpendicular to E, the applied field. Since each electron carries a charge minus E, the total charge transported across this area A to the right in time delta t is minus NEA Vd into delta t. Because let's assume this one particular area here. Within the time delta V, how many electrons are going to move across this area? If you take this particular cylinder, the length is delta x. So within the delta t amount of time, only the electrons in this particular length delta x can make it to this surface because only they have this Vd drift velocity. So the electrons can only travel this much distance in delta t time. So delta x is the distance the electrons can travel in delta t amount of time. So in delta t amount of time, only the electrons which are present in this particular volume can move across this area, right? So that's why we are considering how many electrons will be present in this particular volume, right? So that's what is given here. So this is the total charge, and then you have to add minus E here because that is the charge of one electron. Then this is the total charge transported across this area A to the right in times delta t. The amount of charge crossing the area A in time delta t is equal to I multiplied by delta t because Q equal to I into delta t. So this is nothing but charge. So Q equal to I into delta t. So let's equate these two quantities, and now I delta t equal to NEA Vd into delta t. Now we are just applying the value of Vd here, and we are writing E square A by m into tau n delta t multiplied by E. Now we know that I equal to J multiplied by A because J is nothing but the current density. So let's use this to simplify this equation, and we also know that J equals to, so if you rearrange this equation, if you substitute I equal to J into A and rearrange this equation, finally we get J equal to Ne squared tau by m into E. And this is similar to the Ohm's law which we derived, J equal to sigma into E. So from this we can derive that sigma equals to Ne squared tau by m. So what we did in this case is we just assumed about the conductor with drift velocity of electrons as Vd, and we just substituted the values of current. We just calculated the value of charge in a particular time delta t, and from this we related with the Ohm's law, and we derived an expression for the conductivity of this particular material. So it depends on the charge of electrons and the tau, that is the average collision time, and the mass of the electrons. Okay. Now we are going to define another quantity called mobility. So mobility mu is defined as the magnitude of the drift velocity per unit electric field. So we know what is drift velocity, and divide it by the electric field, then you get mobility. So mobility is given by the units m square by vs. So let's see how we get mobility value. Bd equal to E tau E by m, we already know. Let's substitute it in the equation of mobility, mu equal to Bd by E. So then you get mu equal to E tau by m. So here tau is the average collision time for electrons. So that means how much average time an electron takes between the collisions. Collisions with the atoms or with other electrons. So how much is the average collision time for electrons? It is given by tau. Okay, so we already know what is Ohm's law, and Ohm's law is not applicable all the time. So there are some deviations from the Ohm's law. There are some limitations to Ohm's law. We will see what are those. So though Ohm's law is valid in a wide range of materials, the linear relation between V and I does not hold true in some cases. So V is not equal to IR in all the cases. So we will see what are those cases. In some material, V ceases to be proportional to I. So for example, you see in the lower region, the blue curve and this dotted line stays the same because V is proportional to I. But when current increases, this deviates and goes beyond the linear relation. So this can happen in some materials. So Ohm's law holds true for some current, and when the current is very high, then it deviates. So this is one limitation of Ohm's law. In some materials like diodes, the relation between V and I depends on the sign of V. See, for example, if you look at the positive side of this graph, when V is positive, the graph goes like this. But when V is negative, the graph is going in a different way. So they are not symmetric. They should be symmetric. If they are symmetric, then what will be? It will be like this. It will be going like this. But in this case, it's not very symmetric. So one perfect example for this kind of behavior is a diode. So when you positively bias a diode, then it will give a different value. And when you negatively bias, then it will be a different value. So the relation between V and I depends on the sign of V. The last case is the relation between V and I is not unique. There is more than one value of V for the same current. So in this example, if you see, the voltage increases and the current goes like a curved value. If you look at this point and this point, they both have the same current but different voltages. So this can happen when there are many points like this where the current value is same for different voltages. So, but in linear case, it will not be like that. Each value will have unique current and voltage values. So these are the limitations of Ohm's law. Okay, so we talked about what is resistivity. Why resistivity occurs in a material? Because of the collisions the electron makes with the atoms. And we also derived the formula for resistivity. And while deriving that, we also talked about why resistivity is an intrinsic property of a material. So the resistivity will be different for different materials. So based on the resistivity of values of the materials, we can classify the materials into conductors, semiconductors, and insulators. So metals are conductors and they have very low resistivities in the range of 10 power minus 8 ohm meter to 10 power minus 6 ohm meter. Insulators like ceramic, rubber and plastics have the resistivity 10 power 18 times greater than metals. Semiconductor have resistivity values between these two things, and the resistivity of the materials depend on the temperature. This is also an important point. The resistivity, even though it's an intrinsic quantity, the same material will not have the same resistivity in all the temperatures. And also the metals, semiconductors and insulators, all of them show different behavior with respect to temperature. So they need not be always showing the same behavior. Okay. So now we have um, come to talk about resistance values of resistors. These are the commercially used resistors, and instead of giving the value of the resistors, we have color coded them. So we are going to study how to understand this color codes, and by looking at this color codes, how do we know how much is the resistance value here. So each of this color represents one number, and the first ring and the second ring represents the numbers. The third ring represents what is the multiplier. So how much power 10 the it is going to be. The fourth ring represents the tolerance value or the error value. So for example, see, if it is first two values, if there are four lines like this, we need to just look at the first two values. So both are red in this case. So both red means 2, 2. So it must be 22. And third one is also red. So it's going to be 10 power 2. And silver means 10. So let's see what is the value. So 22 multiplied by 10 power 2 ohm plus or minus 10 percentage. 10 percentage here is the tolerance represented by the silver ring. So let's see what happens in this case. Yellow, violet and brown. So yellow represents 4, violet represents 7, so 47 multiplied by brown represents 1, 10 power 1. So 47 multiplied by 10 power 1, and gold represents 5% tolerance. So the value of this particular resistor is 47 multiplied by 10 ohms plus or minus 5 percentage. So this is how we need to read the color codes of the resistors to understand what is the resistance value. Okay, so when we talked about the resistivities, we also talked about how they are temperature dependent, right? So when temperature increases, the resistivity is also going to change. So how it changes for the materials, we are going to see. So temperature dependence of resistivity. The resistivity of the material seems to be dependent on the temperature. Not all materials exhibit the same temperature dependence. For example, this is a copper. This is a graph of temperature versus resistivity for copper. See, it increases as the temperature increases. So this is the semiconductor where it decreases as the temperature increases. So there are reasons why these materials behave this way, why metals in the resistivity increases with temperature. Because you see, in metals, when you heat up the metal or the temperature increases, the atoms gain a lot of energy and they start vibrating more. So when the atoms vibrate more, then the electrons make more collisions. So the resistivity will be increasing with respect to temperature. But in the case of semiconductors, the free electrons or holes are the charge carriers in the semiconductor. So when you increase the temperature in a semiconductor, you create more number of charge carriers. So that dominates here. So your resistivity decreases when temperature increases in the case of semiconductors. So this is the relationship of rho versus T. So rho T is nothing but the resistivity at a particular temperature. Rho 0 is the resistivity at the reference temperature. So given that you know what is the resistivity at the reference temperature, you can find out what is the resistivity at a new temperature T by using this relationship. Rho 0 multiplied by 1 plus alpha T minus T0. Here alpha is the temperature coefficient of resistivity. So alpha decides how much will be the change in the resistivity when you increase the temperature. So that is given by alpha, and alpha is different for different materials. It's also a material dependent quantity. So now we know rho equal to 1 by sigma, which is equal to m by n e square tau. Now we will see why this resistivity changes with respect to temperature. We derived already sigma equal to n e square tau by m. So by using the drift of electrons and the Ohm's law, we derived this in the previous section. So now we will see what is rho. Rho is nothing but the inverse of this. So m by n e square tau. Now m is a constant. Mass of the electron is not going to change. And what changes here? What are the things that play a role here is the n and tau. Tau is the average collision time. N is the number of charge carriers. As the temperature increases, the average speed of the electrons increases, resulting in more frequent collisions. The average time of collisions decreases with temperature. So this is what happens. So when you increase the temperature, the speed of the electron also increases because they gain kinetic energy and there is more collisions. So the average time decreases. When this decreases, rho increases. That is what happens in the case of metals.
Why waste time in commute and spend lot of money for IIT JEE coaching? Parents, do you want your kids to achieve top scores in IIT JEE? India's leading online NEET coaching 100% success IIT JEE. At TeenEinstein, we focus on IIT JEE coaching from Class 6 to Class 12. We think you'll like it. Our teachers are mostly PhDs in physics, maths, chemistry, botany, and zoology, with lots of years of teaching experience for Class 6 to Class 12. Thousands of videos, quiz, MCQs. We provide a daily worksheet of 30 questions on each topic: math, physics, chemistry, and biology, for rigorous practice, concept understanding, evaluation, quiz, and thousands of videos. Limited offer 40,000 rupees per year. Book your class. TeenEinstein.com